I'm Toru Tanzawa. I'm going to talk about the tutorial on the modeling of the latched AC-DC charge pump based on this work. So let's get started. First, I'm going to talk about the applications of AC-DC or RF-DC charge pumps. Here's the three cases. The first one is the microwave wireless power transfer. So using the antenna, here's the IMS band and the 304, the frequency bands, and the antenna is receive the electron microwave through a matching network. The clock and anti-clock provided to RF and DC charge pump, which output the DC voltage to the load. The second case is used for biomedical application with the much lower frequency range here. So RF generator provides power through the skin, and this the transformer convert input the ultrasonic the energy into the alternate current to RF-DC charge pump to provide the load. In this example, the device for biomedical. The third one is the vibration energy transducer. Using the vibration energy transducer, ambient vibration energy can be converted into electrical power, which drives the IoT sensors through AC-DC charge pump. The frequency is nominally lower than 100 Hz. The AC-DC charge pump looks like this, and as you see, the AC-DC or RF-DC converters has the same the circuit configuration, but with a very wide range, frequency ranges. Therefore, to design the AC-DC or RF-DC charge pump, the unified the charge pump model is required for the wide frequency range. In this, the previous slide I showed a diode. However, the actual diode is used for a different the configuration like this. The first one is the diode connected to single MOSFET. The second is the called as ultra low power diode. So NMOS and PMOS connected in series like this, and so the characteristic is the for the forward bias condition is the same as the single diode case. However, the reverse case, the reverse leakage current is considered to be much lower than the single diode MOSFET case. The third is called the cross-coupled CMOS or CMOS latch, because NMOS and CMOS the connected in cross-couple like this, And also this is simple the latch circuit. So two inverters is connected in one to another, and in between the two capacitors connected. So here's the composed of a unit stage. So in this work, we consider three the variations of the rectifier. So this the slide shows the motivation of this work. When we draw the output voltage versus output current using the cross couple the rectifier circuit, which has this the very high output impedance than the single diode case or ULPD. And original consideration was because cross-coupled the rectifier can have the effectively lower the diode drop, and therefore we should have the simple shift toward the right hand side from a single or LPD curve. However, output impedance was significantly higher than the other cases. And also, this is the previous model, which is well matched with the single diode rectifier. Based on these the conditions, and so when we draw this graph, we came up with the question why output resistance of cross coupler is much larger than the others, and also we must have the specific circuit model needed for cross coupled CMOS the charge pumps than the previous model. First, I'm going to review the previous model of AC/DC charge pump. Here's the circuit, sub-circuit, and the diode is modeled with this equation. And this is about the same as the when the MOSFET is in a subthreshold region, the single diode ULPD latched the charge pump can operate the subthreshold region when the input clock signal amplitude below threshold voltage. So we can use this the current versus voltage relationship for all the three cases originally. And here's the Vn and Vn plus 1 here. So because the DC between the two should be expressed by this, because we have the n plus 1 diodes between the input to PPP, and also this voltage difference we call the VD, diode voltage, can be given by this equation, where the IPP is the average of current, which is the same amount this current that flows every single rectifier. And gamma is defined by the gamma is the conduction angle, meaning when the current is appeared in the time of t on. So t on versus t cycle is the gamma. And average IPP and ID here should be related to this. So with these four equations combined into a single IPP versus VPP relationship like this. So the IPP includes the complicated, therefore you cannot the analytically resolve the IPP equals something VPP. But numerically, you should be able to get the, for example, when you input the IPP, then you will get the VPP using this equation. And this slide, consider the cross-coupled charge bound operating stability region. And let's extend the ID versus BGS, and also let's include the contribution of the BDS. So when you focus on 1, 2, 3, 4, for nodal voltages like this, and V1U up and down, and V2 up and down has the this symmetrical the sinusoid. And also the DC component is the same as before. And BGS and BD. VD is the difference between the two next neighbor capacitor node, which is the 2 BDS, because we have two transistors connected in series between the two capacitors. And here the BGS can be given by this. So if you compare this number as the previous slide, this BGS has no BPP term. So this is a significant difference from the single diode case. These equation can be combined into the IPP-VPP relationship like this. This is a little complicated. However, if the VDS is greater than the thermal voltage VT, and then we can simplify this equation into this. As you see, the right hand side has no VPP term, meaning the IPP has no dependence on the VPP as a current source. meaning a very high output impedance. So this is based on the VGS has no VPP term. Uh, as we have seen before, even though output impedance of the uh, cross-coupled CMOS charge pump is much larger than that of the single diode, but it's still finite, not infinite. Therefore, we must have a little more accurate model is required for the finite output resistance. This is the VGS IDS curve of SPICE model for this circuit, this transistor, and with the different VDS. We called it as the short channel effect. And based on this, the VDS versus saturation current curve, from this, we get the saturation current IS is a function of VDS like this. So using this relationship, so in the previous the equations, we assumed that saturation current has no dependency of IDS, but now we input this relationship in the previous equation for 9 and 10, then these equations is changed, updated with these two equations. And at this point, the IPP versus PPP has so the right hand side incurs the PPP term through VDS. Then basically we have the three the models equations 10, 12, 13, and here's the PPP IPP relationship. So because the measurement our measurement the tools the equipments limited the clock frequency of megahertz range, and so we use these conditions to compare. And here's the SPICE result of the cross-coupled CMOS judgment. And here's the very first model with the infinite output resistance model, and 12 and 13 was the update, and model 13 close to the finite output resistance of the SPICE result. Here's the layout design of single diode ULPD XC, and we have the triple wear process and how the every transistors implemented as shown like this. And here's the die photo. All the capacitors the same among those three charge pumps. And the resistance, the transistors are also equivalent among uh, three the charge pumps. This is the measured waveform with the amplitude of 200 millivolt with 1 megahertz, and so here's the output voltage of three charge pumps. So in this condition, the cross coupler has the highest output, and ULPD was the lowest. Here's the comparisons of IP curves, VPP versus IPP. Here's the amplitude of 400 millivolt, 200 millivolt, 50 millivolt. And the first column shows the SPICE result. Second column shows the measure result. And third column shows the model result. As you see, this color, blue, shows the latch, orange ULPD, and black is a single device. The single device has the highest short circuit current in any VDD condition for SPICE and measure. This is a little different, but mainly the 5 cases, the SD has the largest short circuit current, and the latched charge pump has the largest output resistance than the others. In the 50 millivolt case, the output impedance is about same or as to ULPD. Here's the sorry. And so a single diode case has the largest at 50 millivolt. This probably the SD has the twice larger VDS than ULPD or XC, and therefore when the clock amplitude is very small, then this factor may be the significant contribution to have the high output current. But measure result doesn't show such trend. Another question was the sudden collapse in I out of XC. So this collapse, so model has no such characteristic, but the SPICE and also measured shows that. So this must be investigated to identify the root cause. Because once this happens, the IPP at high VPP is higher with SD than XC. And in the previous slide, the condition was 200 millivolt for the three charge pumps with 10 mega ohm load. And the red line shows the 10 mega ohm IV curve. Then the output voltage is given by the crossing point here. As a result, the latched has the highest VPP and ULPD has the lowest VPP. For the model, when you compare the latched and single, then output resistance increase by a factor of 2 or more. And also this sudden collapse doesn't from the breakdown voltage between the P substrate and NOL, which has the larger than 9 volt, and therefore we must investigate the root cause of sudden collapse. And also, I must say that the threshold voltage of the transistor is about 0.3 volt in this test chip, and therefore the VDD of 200 millivolt and 50 millivolt is makes the transistors the operating subthreshold region. However, the VDD of 400 millivolt, the transistors operate in the weak inversion condition. Using the same data as the previous slide, these the graphs compares the SPICE measure model for the XC, ULPD, and SD with a different VDD. So SPICE and the measured curve very close, 400 and 200 millivolt. The model has about half the short circuit current for the XC and both the SD. The slope of this is about the same here. Mm. This is a comparison of RO short circuit current and open circuit voltage, the XC and SD. And so model shown by gray. The RO is matched within 2x. And here's the ratio between the SD and XC for RO, ISC, and VOC. Roughly, the RO of XC is 2 or 3 than the SD. For the short circuit current, let's see, about the same between the XC and SD. For the VOC, the XC versus SD is over 2. So these result, you can have the rough image like this. short circuit is about the same, but the uh, output resistance is twice or three times larger in the XC, resulting in the largest VOC right here. And therefore, if this is correct, then the XC charge pump can generate the higher output current than SC. In summary, the spice measurement results for XC charge pump showed a much larger arrow than the charge pumps with SD and ULPD switches, raising a big question for us. And therefore, we analyzed the XC charge pump operating in subthreshold region. That analysis suggested that BGS of the transistors has no BBB term, indicating IDS is incest with BBB. However, finite RO is resulted from a weak dependence on the saturation current term on BDS. Then the XCCP model was proposed, which showed the high RO. And RO predicted by the model was included argument with the spice and measure result within a factor of 2 at validity of these ranges. However, this validation was only done at 1 MHz, and therefore we must validate the charge pump's characteristics at different the frequency range, such as 1 MHz or 100 Hz. I put the several references because in the previous slides I just 1, 2, 3 something. Those numbers refer to these publications. That's it. Thank you.